Assalamu alaikum and welcome to lecture number 26. In this lecture we'll continue the topic of the FIR filter design. You understand, in case of FIR filter we need to have the finite number of coefficients. In the previous method where we used the window based method for finding the FIR, we approximated the filter coefficient. For the case we took the ideal filter, and in case of ideal filter in time domain, the impulse response of the ideal filter is infinite. So in time domain, multiplication by a window of finite length will result into a finite impulse response. In this lecture we'll talk about another method, that is the optimal method for the FIR filter design. We continue the topic of FIR filter design. In the previous lecture we used the window method. In the FIR we have finite impulse response, so we should have finite number of coefficients. To obtain the finite number of coefficients, we multiplied the window with the infinite impulse response, because in case of ideal filters the response in time domain or the impulse response is infinite. So we use the window and we obtain the finite number of coefficient. But obtaining the finite number of coefficient from the infinite coefficients, we saw in the previous lecture that there are ripples in the near the discontinuity. So we have ripples in the passband, and we also have ripples in the stopband as shown here. Now in this lecture we are going to talk about another method that is called the optimal method. So we will discuss this method in this lecture. We saw that peak ripple of the filters designed using the window method occurs near the band edges. Like these are the band edges, so here we have peak ripples. Similarly here we also have peak ripples, and we can see or observe here also that the ripple decreases away from the band edges. Like you can see we have ripples with smaller amplitude here, and also we have ripples with smaller amplitude here. Now a better approximation of the desired frequency response can be achieved if ripples are distributed more evenly. You can observe here they are not distributed evenly. So the optimal method is based on the equiripple or same ripple in the passband and the stopband as shown here. So we can see that these ripples have a constant amplitudes both in the stopband and the passband. I think that is very straightforward. You can observe that these ripples, they have a constant amplitude. So it can be observed that the ripples have the same peaks in the passband as well as in the stopband. So in case of optimal method, we want to have equiripple in the passband and the stopband. Shown in the figure here are the practical response, which is H of W denoted here. So we have equiripple in the passband. This is passband. Again, this is the stopband. So we have equiripple here. Whereas in case of ideal, you understand that we have a flat response. So there are no ripples in the passband and no ripples in the stopband. In passband, the practical response oscillates between 1 minus sigma of p and 1 plus sigma of p. Similarly, in case of the stopband, we have equiripple, but they oscillate between 0 and sigma of s. So shown in the bottom of the figure is the error function, which has in case of stop passband has values between sigma of p and minus sigma of p, whereas in case of stopband we have ripples that are between 0 and sigma of p, and this is what we call it the error function. So error function is defined as the difference between the ideal and the practical response, and it is mathematically described as E of W, which is error function. Error is a function of W, or the frequency variable, and this is equal to capital W of W times the ideal frequency response minus the practical frequency response. So I think you can easily spot that E of W is an error function, W of W is a weighting function, HDW is the ideal response, whereas H of W is the practical response. So the in the optimal method, the objective is to determine the filter coefficient such that the maximum value of the weighted error is minimized. That is, we want to minimize, or we want to obtain this function that is minimum of maximum E of W absolute. Then we talk about the parameters that are used for the optimal program. So the parameters for this one are the number of filter coefficients. First we must calculate the number of filter coefficients, then we want to find what is the type of the filter. Basically this J-type filter J-type parameter specifies the type of the filter. So the possible values for the J-type are 1. When we assign it value 1, that means we are using it for the multiple passband or stopband filters, and this includes the filters like low pass filter, high pass filter, band pass filter, and band stop filter. Similarly, if the type of filter is assigned the value of 2, that means you are using it as a differentiator, and if we assign it a value of 3, that means we are using it as a Hilbert transformer. So mainly we'll be using this J-type will be assigned value of 1 because we are doing only for the frequency selective filters, which can be high pass, low pass, band pass, or band stop. The next parameter that we have to assign is the grid density, represented by N grid. So number of frequency points at which the frequency response is checked to see if the optimality condition has been satisfied. So the values N grid can have are 16, 32, or 64. Normally 16 is used, and that's what we call it a default value. So the N grid can have default value of in fact has default value of 16. Similarly, the next parameter is the edge parameter, and this parameter specifies whether the band edge frequencies, so lower and upper band edge frequencies for the filter needs to be specified, the frequencies right. And the important thing about this is that the edge frequencies you specify, they must be in the normalized form, or they must be the discrete frequencies. So you understand how to normalize them. You understand that because if we multiply the continuous time signal frequencies by the sampling period, or equivalently we can also say if we divide the continuous time frequencies by the sampling frequency, then we obtain, right? So continuous time or analog frequency is divided by the sampling frequency will result into normalized frequency or the discrete frequency. The first edge is normally 0 and the last is 0.5. So you understand, if you divide the two things and you get 0.5, that means the dividing thing is twice of the divisor, right? So that means if f of a is your frequency, so if f of a divided by f of s results into 0.5, so that means you are going for the maximum sampling frequency, right? So at maximum, sorry, a half of the sampling frequency. The maximum number of bands, that is pass band and or stop band, supported by this is 10. So that means you cannot exceed the uh, value of 10. The first parameter required to use the optimal program is the number of filter coefficients. Now the number of filter coefficient is not known, so to find the value of the number of coefficient to be used, we must estimate it using empirical relationships. So there are different methods. So one of the method is low pass filter. For the low pass case, that is Harman et al. They proposed in 1973. So based on this method, the number of coefficient equals to d infinity function of impulse of p and impulse of f over delta of f minus f function of impulse of p, impulse of s multiplied by delta of f plus 1. So you understand that delta f is here to denote the width of the transition band, and it must be noted that it should be normalized, that is it should have the value of the discrete the delta of f, which represents the width of the transition band. It must be in discrete form. So to obtain a discrete form, you understand, you will divide whatever is given to you by the sampling frequency. So if you are given the transition width of the transition band, simply dividing it by the sampling frequency will result into the transition band in normalized form. Okay, the second is the d infinity function of impulse of p and impulse of f. So this is given as log of impulse of s into a1 log of 10 impulse of p square plus a2 log of 10 impulse of p plus a3 plus a4 log of impulse of p to the base 10 square plus a5 log of 10 impulse of p plus a6. And similarly, the f function of impulse of p and impulse of f is given as this value plus 0.5124 log of impulse of p to the base 10 minus log of impulse of s to the base 10. You understand the impulse of s and impulse of p, they are basically the ripples in the pass band, in the stop band and pass band respectively. Whereas the values for a1, a2 are, these are the values which are constant. So by putting these values and knowing the requirement, that whatever requirement we have, you understand, in case of the filter design, we first need the specification where it is mentioned what should be the pass band ripple, what should be the stop band ripple, and so on. So with the given number of these specification, by putting them into this equation, we get the rough estimate of the number of coefficient required for the proposed filter. Similarly, for the case of the bandpass filter, the procedure proposed by Mintzer and Liu back in 1979 is given here. So the number of coefficients required for the bandpass filter are C infinity function of impulse of P and impulse of F or delta of F plus G function of impulse of P and impulse of S into delta of F plus 1. So here to find the C, which is function of impulse of P, right? The passband and stop band ripples. So this is equal to, I think that's quite visible. I think you can easily see this. So just these are the terms involved. So because we already know impulse of P, because while designing the filter, so we know impulse of P and impulse of S. So we can straight away find, right, impulse of S and impulse of P we are given. So the rest are the coefficients that are constant. So values for B1, B3 up to B4, and values for the A1, A2, A3 as also mentioned in the previous slide. So we can easily find the C impulse of C infinity function of impulse of P and impulse of S. So we can easily find that one. The second parameter is delta of F. So delta of F is again given because delta of F is basically the transition width. So while for designing filter we are given the filter specification, and one of the specification is the transition width, and remember that this transition width is in normalized form. So if it is not already in normalized form, simply dividing it by the sampling frequency will result into delta of F. And similarly G function of impulse of P and impulse of F is defined here. So I think that's very straightforward. Just using a calculator you can, provided you are given the value of impulse of P and impulse of S, that is pass band ripples and stop band ripples. Knowing this, we can easily find the value of this one and value of this one, and simply summing this with this plus 1 will give us the rough estimate of the number of filter required for the given specifications. So for minimize max EW value, the resulting filter response will have equiripple in pass band and stop band. So for a linear phase low pass filter, there are R plus 1 or R plus 2 extrema. Extrema means the minimum or the maximum values. So R can be found using the expression R equals to n plus 1 over 2 for type 1, right? And you understand n is basically number of coefficients which you have found in the procedure as described in the previous slides. The extremal frequencies are indicated by small circles, like this one is a extrema, this one is extrema, and so on. So these are all the extremas in the pass band. Similarly, the extrema in the stop band are indicated here. So the simplified flow chart for the optimal method is as shown here. First, you have to specify the requirements of the filter and determine program inputs, right? So with the specification of the filters, you can find out the number of filter coefficients. Once you have these, then you can find the value of R, and then using that R you find the extrema, then you determine the EFW and its largest R plus 1 extrema. Now if extrema changes, then you repeat this step and you keep on changing this until you get a constant. Once you get a extrema constant, then you get the H of W, the practical response, and knowing the practical response H of W, simply taking the inverse Fourier will result into the desired filter coefficients. The locations of the extrema frequencies are important. So, but we see that the only location of extremal frequencies available or we can find is the band edge frequencies, where we know, but for the other cases we don't know the locations of the extremal frequencies. Hence the main problem here is to find out the locations of the extremal frequencies. So to find the extremal frequencies, there is a powerful algorithm which is based on Ramey's exchange algorithm is developed, and using this algorithm we can find the extremal frequencies, the locations of the extremal frequencies. So once we know the locations of the extremal frequencies, then it's quite straightforward to find out the filter coefficients. So summary of the optimal method is presented here. Step 1 is the specification of the band edge frequencies, that is band pass and band stop frequencies, pass band ripples and stop band attenuation. You know that they may be in ordinary units or they may be in decibels, and the importantly is the sampling frequency. So you understand that basically these problems, involved that we are given the band edge frequencies and all those important specifications in the continuous frequency. So we have to convert them to the digital or discrete or normalized frequency. So the second step is the frequency normalization. So we have to normalize each band edge frequencies, and you understand how we can do it. So if we are given the sampling frequency, so simply we divide the frequencies by the sampling frequency to obtain the normalized values, such as for the edge band, for the transition band, for the pass band, or the cutoff frequencies, etc. Or if you are given the sampling period, so simply multiplication of the sampling period by the analog frequency will result into the frequency normalization. The third step will be use the passband ripple and the stopband ripple attenuation expressed in ordinary units and normalized transition weight to estimate the filter length. So you understand how we can estimate the filter length or the number of filter coefficients required. So I think we have talked about the band pass and the low pass filter on the previous slide, so that's quite straightforward, that only knowing the ripples in the stop and pass bands and the stop band attenuation, etc. I hope you are now well familiar with these terminologies. So using those we can empirically determine the values, that is the filter length. Okay, so the important thing is that typically the value of n, the length of the filter required to meet the specification, would be slightly higher, maybe 2 or 3 times than the value determined from these equations. The fourth step would be to obtain the weights for each band from the ratio of the pass band to the stop band ripples, or to vice versa, that is stop band to the pass band ripples expressed in ordinary units. It is convenient to express the weights for each band as an integer. For example, a low pass filter with a pass band and stop band ripples of 0.01 and 0.003, pass band ripple and stop band attenuation of say 0.09 dB and 30.5 dB respectively. Okay, so these are the ordinary numbers, they are in the, and these are in the decibels. So would have for such a case would have a weight of 1 for the pass band and 3 for the stop band. Okay, that's 0.01 divided by 0.03. So you understand this will cancel, so you'll get 1 over 3. So this may be read as weight of 1 for the pass band, and you understand because or maybe I just write here, so you understand that I can write this something which is 0.01 and 0.03. So in the ratio I can write it impulse of P or impulse of S. So 0. So I hope you understand that this cancels with this one, so we are left with 1 by 3, or you can also say that you just multiply this one by 100 to get right. So multiply by this 100 will result 1, right, and similarly multiply this by 100. So because you are multiplying, so you are also dividing, right? So I hope you are quite familiar with decimal fractions. So that's straightforward. You get this thing. So that means you have a weight of 1 for the pass band and weight of 3 for the stop band. Band pass filter derivations, right? Sorry, not derivation, in fact deviations, that are ripples of, for example, 0.01 in the pass band and 0.0105 for each of the stop bands, right? You understand we have band pass, so we have something like this. Let me draw. So here as given, band pass filter deviations ripples of the 0.001 in pass band and 0.0105 for each of the side bands, they are mentioned here. So for example, this is a band pass filter, so it has, you understand that in case of band pass filter we have 1 pass band and 2 stop band. Now it is mentioned here that each of the stop bands has this value, right? Ripples of this value 0.0105, right? So in this case, in the ratio, we can write it like this. So if we simplify, it will be something like 0.001 divided by 0.105. So that's basically 10 over 100. So if we simplify it, so that's 2 over 21. So that means for each of the stop bands would have weights of 21 for the pass band and 20 for the stop band 21, and for the pass band we have so we have for each of the stop bands, right, would have weights of 21 for the pass band, right? So as indicated here, because this is the ratio of ripples in the pass band or ripples on the stop band, so we have ratio of this one. So that means for stop band we have for the pass band we have 21, and for the stop band we have 2. So the weights for the stop bands will be 2. So in fact weight of 2 will be assigned to this one and to this one, whereas for this case we have weight of 21. Okay, then the fifth step is input parameters to the optimal design program, right? So we'll input the parameters to the optimal design program to obtain the coefficients and band edge frequencies and the weights for each band together with the suitable grid density. Okay, so as we have talked about all of these, so suitable grid density can be 16 or 32 or maybe 64. The default is 16. Okay, so inputting all these information to the program, we'll get the coefficients. Then we check the pass band ripples and the stop band ripple attenuation produced by the program. If the specifications are not satisfied, increase the value of the n, that is the number of the filter coefficients, and repeat these above mentioned steps until until they are then obtained, and check the frequency response to ensure that it satisfies the specifications. Okay, so we up to step 5 we go. That means we input all these information and we give it to the optimal design program, and we find, right, at step 6 we check the passband and stopband ripple attenuation produced by the program. If this is satisfied, then that's all. This is the from here you can find out the coefficients of the filter. But in case they are not satisfied, then you have to increase the number of filter coefficients and redo these steps. So I hope this gives you the idea. So let's take a numerical example and see how we can use the optimal method to design the filter. So in a given problem, a linear phase bandpass filter is required to meet the following specifications. So we have a passband that is 900 Hz to 1100 Hz. You understand the continuous signal frequencies. So with the passband ripple of 0.87 dB, the stopband attenuation greater than 30 dB, sampling frequency of 15 kHz, and transition of 450 Hz. So this is the graphical representation for the problem. So the second step would be, because the first step is that you have been provided the specification. The second step is to normalize these frequencies. Okay, so graphically we can see we have this type of filter we have in continuous frequency domain. This is the passband. We have the passband ranges from 900 up to 1100. We have the transition frequency, that is 450 Hz. So this is 450. So from 450 up to 900 we have one transition band, and from 1100 up to 1100 plus 450 we have another transition band. Okay, so the first step is that we normalize these frequencies. So starting with 450 Hz, so you understand normalization is achieved by dividing the frequency by the sampling frequency, or if you are given the sampling period, then multiplying the by the sampling period. So both are same. Okay, so we get this value 0.03. So this is the frequency for the this point. Okay, then again the next point is 900. So again we normalize this one, so we get 0.06. So this corresponds to 0.06. The next is 1100. So 1100 divided by 15k will result into 0.0733. So this basically corresponds to 0.0733 in normalized frequency. The next point is this one, which has frequency of 1550. So the normalized frequency for this will be 0.033, and for this point the frequency will be 7500. So 7500 divided by 1500 will result into 0.5. So this is the point where we have frequency of 0.5. Okay, and you understand, again we'll have another replica of this one that will be around 1. Okay, because we are taking the normalized frequencies for the case of linear frequency. You understand the relationship between the linear frequency and the angular frequency, that we write omega for the angular frequency and we write omega equals to okay, let me write the continuous time case. So in continuous time case, omega equals to 2 pi f. Okay, so similarly for the discrete time case, it will be equal to 2 pi by the sampling 2 pi f divided by the sampling frequency, which is okay. So we can obtain the angular frequency, or we can also obtain the discrete or normalized frequency in terms of linear frequency. So I hope that's straightforward. Okay, and again you understand, because the sampling the continuous time signal, right? In time domain, sampling results into the replicas of this in the frequency domain. So again we have another replica here around 1. Okay, this whole thing, similarly we'll have another replica of this one around -1, and so on. I hope that's we have done this while doing the sampling of continuous time signal. So based on those concepts, I think that's straightforward. Okay, so that's the second step. Thus we obtain the normalized bands, which are 0 to 0.03, this band, right? This is 0 to 0.03. Okay, that's the stop band. Okay, this is stop band, and again this is stop band, right? And you understand this is the transition band. So we have two transition bands here. Okay, so we have stop band, transition band, pass band, transition band, and stop band. Okay, so the normalized values for the first stop band will be 0 to 0.03. Then we have the pass band, which has normalized frequencies of 0.06 to 0.0733. Again we have another stop band, and that stop band, this one, so this has frequency range of 0.1033 to 0.5. okay, and these replicas are repeated. Okay, so again around 1 we'll have same type of thing, something like this. Okay, and like this. Okay, so that's straightforward. So the third step would be to find the length of the filter, and the fourth is finding the weight. So maybe we can interchange the third and fourth step. So let's first find the weights for the bands. Okay, so you understand this is also quite straightforward, that we are given the ripples in dB, so they can be expressed in simple numbers. So you understand that 0.85, you can take anti-log of this, and basically this is a relation. So you can just divide this by 20 and then take the anti-log of both sides, so which will result into the passband ripple of something like this. And similarly for the stop band attenuation, we have this one. So from here we can easily find the ripples in the stop band also. So you understand, to find the weights for the bands, we can write them, for example, like this one, ripples in the pass band or ripples in the stop band. This corresponds to stop band weight over the pass band weight. You can also write in the opposite way, that you express it like impulse of S or impulse of P. In that case you have to write this is equal to pass band weight over the stop band weight. So this is, I think, pretty straightforward arithmetic. So we can find the weights like this. So we could use the weight of 3 for the pass band, okay, and weight of 10 for the stop band. Okay, and we can also quickly find the length of the filter using the equation that is provided in the previous slides. You can go through it. So simply we can, by putting the values there, we can putting values of the impulse of S and impulse of P and the transition width, so we can easily find the length of the filter, which comes to be roughly 40. So we'll use n equals to 41. Now the input to the optimal program can be summarized as filter length will be equal to 41, type of filter, that is J type, that's equal to 1 for the band pass, high pass, low pass, and band stop. Okay, 1, and you understand other values for the other type of filters. Then we write weights. So we have weights of 10, 3 and 10. Okay, so stop band, pass band, and again the stop band. And maybe we take the number of grid points 32, you can also take 64 or 16. Okay, and then we take the edge frequencies that are also input to the program. So these are the edge frequencies as we found in the previous slide. Thus providing the those values to the optimal program will give us the resulting filter coefficients. So I think that's again quite straightforward, but that's also needs some programming language. So in this book they have given the examples code to find the filter coefficients. So I would like that you should go to the example 7.7 and find the filter coefficients, also explore the codes. I think you can find the one for the MATLAB, and because you are now good at MATLAB, also this program doesn't require very much expertise, so that's quite straightforward, and I hope you can easily implement it. Anyway, go through the example 7.7 and we'll discuss it in the live session. So with this we end the lecture for today and see you in the live session. Okay, Allah Hafiz.